In this section, we will discuss graphing of functions using calculus. Especially, we will be discussing rational functions. The concepts required are already familiar to you. I will just summarize them. First concept required is the increasing and decreasing nature of functions. So we know that a function f is said to be increasing at a point x naught if f dash x naught greater than 0, and if f dash x naught less than 0, the function decreases at x naught. This is the first derivative test, and of course if f dash x naught equal to 0, the test is inconclusive. So observe that if f is increasing, then the graph will be any one of the two on the right side. It can be either this or this one. So in each case, note that the tangents drawn to any point on the curve is landing to the right and has positive slope. Similarly, if f dash is negative or if f decreases, then the second row curves are the curves for the corresponding graphs, and the tangents have negative slope as it is landing to the left. So generally, if f dash x is positive in an interval, then f increases in the interval, and if f dash is negative in an interval, then f decreases in the interval. Next concept is the critical points. These are the points where either f dash vanishes or f dash does not exist, with some additional conditions which you are already known. Third one are the extreme values. So you are already familiar to the concepts of local maximum, local minimum, and global maximum, global minimum values. The extreme values are the points where the function attains its extreme values. I mean, the global extreme is the maximum value of the function it attains in the domain, and similarly the global minimum. The local maximum or local minimum are the values which are maximum or minimum in a given interval. So observe that a function attains its maximum or extreme values either at the endpoints or at the critical points. So provided the function, the domain of the function is a closed interval, it can attain the extreme values either at the endpoints also. So we have the first derivative and second derivative test to determine the extreme values or local maximum, local minimum of a given function. So the first derivative test is if x naught is a critical point and f dash changes sign from positive to negative at x naught, then x naught is a local maximum point. And if f dash changes sign from negative to positive at x naught, then x naught is a local minimum point. So observe that if f dash changes sign from positive to negative continuously, because f is a continuous function, and we assume f dash also is continuous. So if it changes sign from positive to negative, then there will be a stage where it attains a zero slope also, and that is a critical point. Okay, so also note that to change sign from negative to positive, the tangent must be changing its landing from right to left. Okay, so look at the picture on the right side. So that shows there is a local maximum point. And if f dash changes sign from negative to positive, then x node is a local minimum. That is, the slope of the tangent changes from negative to positive continuously. So the slanting changes from left to right. So naturally there is a local minimum. So the first point, f dash changes sign from positive to negative, means f dash, the values of f dash is decreasing, and hence its derivative, that is f double dash, must be negative. And if f dash changes sign from negative to positive, then it is increasing as it changes from negative to positive, and therefore its derivative f double dash must be positive. And this is the motivation for the second derivative test. It is if x naught is a critical point and f is twice differentiable, then if f double dash is negative at x naught, then x naught is a local maximum point, and if f double dash x naught is greater than 0, then x naught is a local minimum point. The fourth concept is the concavity of a curve. We have the concepts of concave up and concave down. A function is said to be concave up in an interval if it lies above all the curves, all the tangents to the curve in the interval. And if it is lying below the tangents, then it is concave down. Look at the pictures. The first two are for concave up because all the tangents are below the curve, or the curve is above the tangents. So it is concave up. Similarly, in the second set of pictures, all the tangents which are drawn in green ink are above the curve, or curve is below the tangents. Therefore, the curves are concave down. So if the function is concave up, f dash increases, and if the function is concave down, f dash decreases. This is very clear from the two set of pictures given just above. So we have the second derivative test for concavity. F dash increases for concave up. Therefore, if f double dash x is greater than 0, then f is concave up at x naught, and if f double dash is less than 0, then f is concave down at x naught. Next is the points of inflection. These are the points where the concavity changes. That is, if the concavity changes from up to down or from down to up at a particular point, then it's a point of inflection. So naturally, concavity depends on the sign of f double dash. So the points of inflection will be the point where f double dash changes sign. So it is at an inflection point either f double dash equal to 0 or f double dash does not exist. Okay, moreover, if f double dash exists and is continuous, then x naught is an inflection point if f double dash x naught equal to 0 and f triple dash x naught is different from 0. But merely the second derivative equal to 0 does not mean it's a point of inflection, because if you consider f of x equal to x power 4, the graph of which is parabolic, then it is always concave up. But at x equal to 0, f double dash equal to 0, also f triple dash also is 0. And since it is always concave up, there is no point of inflection. So the two ways of finding a point of inflection is either use this test, that is find out f double dash, f triple dash. If f double dash is 0, then find out f triple dash and prove that it is different from 0. Or else find out the points where f double dash equal to 0 or f double dash does not exist, and see whether it changes sign, that is to the points on the left of x naught and the points on the left of right of x naught. If f double dash changes sign, then x naught will be a point of inflection. We will see this in the examples below. And one more concept is the asymptotic behavior of functions. In layman concepts, the term asymptote simply means tangent at infinity. So if a branch of the curve, or if the curve itself tends to some straight line but never touches it, that means we feel that the curve touches some line at infinity, then that particular line is an asymptote. That is why we call it as a tangent at infinity. We have the concepts of vertical asymptotes, horizontal asymptotes, and oblique asymptotes. So particularly x equal to x naught is a vertical asymptote if limit extending to x naught f of x equal to plus or minus infinity. And y equal to L is a horizontal asymptote if limit extending to infinity f of x equal to L. And we will see how we can deal with oblique asymptotes. The final concept is even and odd functions. A function f of x is said to be an even function if f of minus x is f of x itself, and odd if f of minus x is minus f of x for every x. Example, f of x equal to cos x is an even function, whereas f of x is sin x is an odd function. So we have the combinations of even and odd functions. For example, sin x plus cos x. It is neither even nor odd. And any polynomial function in which each term is of even degrees, we consider constant as a term with degree 0, which is even. Then the function is even. And if each term of a polynomial is of odd degree, then the polynomial is an odd function. For example, x cube plus x is an odd function, whereas x square minus 2 is an even function. So the major point to be noted is that if a function is even, then the graph of the function is symmetric about the y-axis, and if a function is odd, then the graph of the function is symmetric about the origin. Okay. Then the next section is the drawing of graphs. This is the major topic that we are going to deal in this section. In this video. We will discuss a 6-point procedure to draw the graph of any given polynomial function or rational function in particular. To sketch the graph of a given function y equal to f of x, we follow the 6 steps below. So the first step is identify if the function has any symmetries. That is not that if the function is even or odd. If it is even, symmetric about y-axis. If it is odd, symmetric about the origin. The second step is identify the asymptotes, if any exist. Third one is identify the critical points, which in other ways determines the intervals where the function increases, decreases, the local maximum point and the local minimum point. And in step 4, we identify the points of inflection, if any are there, and in other ways we are determining the concavity of the function. In step 5, we gather all the information from step 1 to 4, and using them, we draw a rough sketch. And finally, in step 6, we locate some points on the curve, and using the rough sketch in step 5 and the points located already, we will draw the original graph. So let us discuss illustrate with certain examples. So the first example is graph the function f of x equal to 1 by 6 x cube minus 6x square plus 9x plus 6. So step 1 is identification of the symmetry. So f of minus x is neither minus f of x or f of x. Therefore, it is neither even nor odd. So there is no symmetry. Okay. Then identifying the asymptotes. So we have already noted that it has a vertical asymptote x equal to x naught if limit extending to x naught f of x is plus or minus infinity. Or in other words, if there are certain points where the function is not defined, then that particular point is an asymptote, vertical asymptote. For example, 1 by x. Then this is not defined at x equal to 0. Therefore, x equal to 0 will be a vertical asymptote. Okay, for f of x equal to 1 by x. So here limit extending to x naught is f of x. Limit extending to x naught f of x is defined for all x. That is, it is never plus or minus infinity, and therefore it has no vertical asymptote. And limit extending to infinity f of x is not a finite quantity. It is infinity. Therefore, it has no horizontal asymptotes also. In step 3, we identify the critical points. So f dash of x equal to 0 will imply half of x square minus 4x plus 3 equal to 0, which identifies x as 1 or 3. So f dash x can be written as half of x minus 1 into x minus 3. So we can say that the possible critical points are x equal to 1 and x equal to 3. So we will now, what we do is we split the entire real axis from minus infinity to infinity into 3 at x equal to 1 and at x equal to 3. So what we have done is we have drawn the real axis, and at 1 and 3 we marked it. So we split from minus infinity to 1, 1 to 3 and 3 to infinity. Okay. So critical points are x equal to 1 comma 3. Then there are two ways of identifying the increasing decreasing nature. That is, either we substitute a point from minus infinity to minus 1, again 1 to 3 and 3 to infinity in f dash of x, and determine the sign. For example, 0, f dash of 0, it is between minus infinity and 0. F dash of 0 is positive, therefore f increases in minus infinity 1. Again 1 to 3, find out f dash of 2. So again it is negative, therefore the function decreases. And from 3 to infinity, for example, say x equal to 4. So f dash of 4 is positive, therefore f is increasing. Or else we determine the sign of each of the factors x minus 1 and x minus 3 and plug into f dash of x. So in minus infinity 1, x minus 3 is negative, x minus 1 is negative, and therefore sign of f dash is positive. That is what I have written here, or you can do the other way too. So therefore f is increasing in minus infinity 1. Similarly in 1 3 it is decreasing, and in 3 infinity it is increasing. Note that I have made a mistake already. I have corrected it. So note that minus infinity 1 increases, 1 to 3 decreases, and 3 to infinity increases. So x equal to 1 is a point of local maximum, and x equal to 3 is a point of local minimum. In step 4, we identify the inflection points, which determines the concavity. So find out f double dash, it is x minus 2. So f double dash will exist for every x. F double dash equal to 0 implies x equal to 2. And naturally, f triple dash equal to 1, so not equal to 0. Therefore, x equal to 2 is a point of inflection, which means on x equal to 2, the concavity changes. So sine of f double dash to the left of 2 is negative, therefore the function is concave down in minus infinity 2 and positive in 2 to infinity, therefore it is concave up there. Okay, so in step 5 we collect the information from steps 3 and 4 and draw and consolidate them. Like I have drawn the entire real line and plug the points or mark the points 1 3, which are the critical points, and 2 the inflection point on the real line. So the real line is split into minus infinity 1, 1 to 2, 2 to 3, and 3 to infinity. So it is split into 4 subintervals, and we mentioned the nature of f of x, like increasing, decreasing, and concavity in these intervals. So in minus infinity 1 it is increasing and concave down, 1 to 2 it is decreasing and concave down, 2 to 3 it is decreasing and concave up, 3 to infinity it is increasing and concave up. So the possible pieces of the curve is given there. So joining these 4 pieces, we have a rough sketch like this, which I have mentioned there. Okay. So these possibilities are mentioned here. So if it is concave up and increasing, then this curve, this is the curve which can be drawn, which is the possible curve, which is concave up and increasing. And if it is increasing and concave down, this is the possible curve. Okay, if it is decreasing and concave up, then this is a possible curve, and if it is decreasing and concave down, it is the possible curve. Okay, in step 6 we locate some points on the graph or on the curve, and using the rough sketch and the points we have located, we will draw the original curve. So note that we must include the points, critical points, as well as the points of inflection in locating the curve. Locating the particular points on the curve. So x equal to minus 1, 0, 1, 2, 3. 1, 2 and 3 are must, because 1 and 3 are critical points and 2 is the point of inflection. So joining them, we have the curve as shown here. As a second example, let us consider the graph of x minus 1 by x. So it is symmetric about the origin because it is an odd function. So what we need to study is study the curve only for x greater than or equal to 0 and then reflect the graph in the y-axis first and then on the x-axis. And we can see that it has no vertical asymptote, no horizontal asymptotes, and x equal to 0 or the y-axis is a vertical asymptote. Also, for large x, 1 by x is 0. That means x minus 1 by x will tend to x for x tending to infinity, or y will tend to x as x tending to infinity. That is, the function x minus 1 by x behaves just like x as x tending to infinity. Therefore, y equal to x is an oblique asymptote. I have explained another example at the end of the section. In step 3, we identify the critical points. So we note that f dash is 1 plus 1 by x square, which is positive throughout when x not equal to 0, and at x equal to 0 it does not exist. So x equal to 0 is a critical point, and since f dash x is greater than 0 for every x, of course different from 0, f is increasing throughout. Okay, so it has no extreme values. Then step 4 is the concavity. F double dash of x is minus 2 divided by x cube. Minus 2 by x cube is less than 0 for every x greater than 0. Because it is an odd function symmetric about the origin, we need to consider only x greater than or equal to 0. Okay, which we have already mentioned. Since it is negative, f is concave down on 0 infinity. Okay, and since it is always increasing, there is no point of inflection. Roughly sketching, we have the curve like this. Curve will be looking like this. This is the oblique asymptote, and this is the vertical asymptote, and this is how the curve will look like. Okay, and gathering all the information from step 5 and finding some points on the curve, we have the curve like this. First, what we have done is we have drawn the curve using the rough sketch and reflected it on the y-axis and then on the x-axis. As a third example, draw the graph of y equal to x divided by 1 plus x square. So note that f of minus x is minus f of x, so it's an odd function, hence symmetric about the origin. So again, we need to consider for x greater than or equal to 0 only and reflect about the y-axis and then on the x-axis. So again, since x divided by 1 plus x square is defined for every x, there is no vertical asymptotes. And as extending to infinity f of x equal to 0, that means y equal to 0 or the x-axis is a horizontal asymptote. Again, f dash x equal to 0 implies x equal to plus or minus 1, which implies 1 and minus 1 are the possible critical points. Again, we find out the sign of f dash of x on the intervals minus infinity to minus 1, then minus 1 to 1 and 1 to infinity. And note that in minus infinity minus 1 the function is decreasing, minus 1 to 1 it is increasing, and 1 to infinity it is decreasing. Therefore, minus 1 is a point of local minimum and 1 is a point of local maximum. And in step 4, we identify the inflection points. So f double dash is 2x into x square minus 3 divided by 1 plus x square the whole cube. So, it exists for every x. So the other end is f double dash of x equal to 0, which implies x can be 0, root 3 and minus root 3. These are the 3 possible points of inflection. So let us see the change of sign of f double dash. So what we do is we will split the entire real axis into 4 from minus infinity to minus root 3. Again, minus root 3 to 0, 0 to root 3 and root 3 to infinity. Note that it is concave down in the first interval, again up in minus root 3 0, down in 0 root 3 and up in root 3 infinity. So it changes concavity at all these 3 points, and hence all the 3 points 0 plus or minus root 3 are points of inflection. Okay, then the possible curve roughly we consolidate from steps 4 and 3 and 4. So in the so what we do is the entire real line is split into the points, the critical points as well as the points of inflection. So only we have the critical point is x equal to plus or minus 1. So we have 5 points which divides the entire real line into 6: minus infinity to minus root 3, minus root 3 to minus 1, minus 1 to 0, 0 to 1, 1 to root 3, and root 3 to infinity. And in each of the interval, minus infinity to minus root 3, it is concave down and decreasing, etc., etc. So we have these pieces of curve as mentioned. So combining them, we have a rough sketch like this. Okay, so observe that here the function increases concave down. Again, there is a point where it changes, it is concave down again but decreases, and again there is a point where it changes concavity, etc. Okay, and using the information on step 5 and locating some points on the graph, okay, we draw the graph. We need not include the negative points because it is symmetric about the origin, so we consider only the points for x greater than or equal to 0. And what we do is we reflect the graph first on the y-axis, which I have mentioned or drawn using these dotted lines in green ink, and then that portion is reflected on the x-axis. So we have this darkened or thick curve is the required graph of the function. As an example, we draw the graph of f of x equal to x raised to 5 by 3 minus 5x raised to 2 by 3. So it is not symmetric about any of the axes or origin, since it is neither odd nor even. Then the function can be written as x power 5 by 3 into 1 minus 5 by x, which is defined for every x, so there is no vertical tangent. But also as extending to infinity, there is no horizontal tangents too. Again, critical points are it is not defined at x equal to 0 and equal to 0 at x equal to 2, because x raised to minus 1 by 3 is not defined for x equal to 0. So x equal to 0 and 2 are the possible critical points. So we will find out the sign of f dash in minus infinity 0, in 0 to 2, and 2 to infinity. So we have seen that it increases in minus infinity 0, decreases in 0 2, and increases in 2 to infinity. And concavity f double dash is defined for every not defined for every x. It is not defined for x equal to 0 and it equal to 0 at x equal to minus 1. So these are the x equal to 0 and x equal to minus 1 are the two possible points of inflection. And by finding the sign of f double dash, we have seen that it is negative in minus infinity minus 1, so it is concave down. Minus 1 to 0, it is positive, therefore concave up. And again 0 to infinity, it is again positive, so concave up. So observe that the concavity changes only at minus 1, changes from down to up in minus 1, and there is no change of concavity at x equal to 0. So the only point of inflection is x equal to minus 1. So now we consolidate all the points noted in steps 3 and 4. So we see that in minus infinity minus 1, it is concave down and increasing, minus 1 to 0 concave up and increasing, and 0 to 2 it is concave down and concave up and decreasing, and 2 to infinity it is concave up and increasing. So this is a possible general shape of the function, but it is something different. It is just possible rough sketch of the graph. Now locate some points and clubbing all the information collected together, we have the graph of the function like this. And as a last example, I have found an asymptote for the function f of x equal to x plus 1 by x. So note that it is not defined at x equal to 0. Therefore, x equal to 0 is a vertical asymptote. Again, as extending to infinity, the function tends to infinity. Therefore, no horizontal asymptotes. But note that as extending to infinity, 1 by x will tend to 0. Therefore, x plus 1 by x will behave like x plus 1 itself. That means y equal to x plus 1 is an oblique asymptote. So here we say that as extending to infinity, the term x plus 1 dominates the term 1 by x. So in such cases, y equal to x plus 1 or such terms are the oblique asymptotes.